Hello and welcome to part 4 of our lithium batteries lecture. In this video we deal with the electrode material conductivity. Compared to electrodes in lead-acid batteries or also in alkaline battery systems, the intercalation electrodes used in lithium-ion cells are so-called continuum electrodes. The redox reaction occurs in the active material volume. After moving from the electrolyte into the active material, the lithium ions must then move to their sites in the grid. It's both the ionic conductivity of the electrolyte and the electrodes, as well as the electrical conductivity of the electrons and electricity collectors, are factors. The ion conductivity of the SEI, solid formed, also must be taken into account. To ensure electrical contact between the individual active particles, these are mixed with a conductive material, a good electrical conductor such as carbon, for example. As a result, most electrodes used in lithium-ion cells should be viewed as complex, porous, composite materials. The diffusion of condensed materials, solids and liquids, is generally caused by the transportation and transposition of atoms or ions due to random thermal motion. Solid diffusion can be attributed to various mechanisms. Due to their small radius, lithium ions can easily diffuse through grid intersticks. Lithium-ion mobility is determined by the solid structure, binding characteristics and possible defects. Depending on the diffusion path created in the crystal, structures with tunnels aligned in single direction 1D, with layers 2D, and with tunnels aligned in 3 directions 3D with nodes may result. Lithium ferron phosphate exhibits a typical 1D structure, whereas the lithium nickel manganese cobalt or the lithium cobalt, a layer structure 2D is formed, and with lithium manganese a typical 3D structure is get. This explains the diffusion coefficient listed in the table below here. If lithium ions can easily diffuse between the layers 2D, as with the lithium cobalt, then diffusion coefficients at the highest range between 10 to the minus 10 to 10 to the minus 8 square centimeters per second result. Comparison of these diffusion coefficients with those of the electrolyte demonstrates that lithium-ion diffusion into the active materials is significantly lower. There are a range of options for influencing diffusion. One option is to dope the material. This approach alters in electrical band structure to facilitate lithium-ion diffusion. Another option is to shorten the diffusion path by reducing particle size as well as altering particle morphology and form, for example, a flattened form. The ratio of surface area to volume can be changed by altering particle size or particle form. A larger surface area and shorter diffusion paths, several smaller particles instead of one larger particle, facilitate charge exchange and diffusion. If active materials containing carbon are used, the SEI formation on the negative electrode side must also be taken into account. Since it has a lower diffusion coefficient than the active material, it increases the ionic resistance. In addition, lithium-ion intercalation in graphite is a special case. There are several intercalation stages, which are seen as small plateaus in the open circuit voltage curve. But with non-graphite amorphous carbons, no intercalation stages are observed. Interestingly, amorphous phases have poorer electrical conductivity than the graphite phase, but better diffusion characteristic. And as a result of that, diffusion can be precisely adjusted by varying the percentages of graphite and amorphous phase, carbon black for example. Compared to graphite in the negative electrode or metallic electricity collectors, aluminium, copper, the materials used on the positive electrode side oxide, spinel, phosphate, have a conductivity several orders of magnitudes lower. In addition, these materials are semiconductors. This means that their conductivity is thermally activated. Doping the active material particles to increase conductivity, coating the electrode particles to increase electrode conductivity, and reducing particle size, analog diffusion. The most effective approach to coat the active material particles in the submicrometer or nanometer range, for example with the carbon. And now in the next video we go and look how those batteries look from outside. Thank you very much.